CODAIT. We have Fred today from CODAIT as well, Center for Open Source Data and AI Technologies, which is going to be talking about Elyra and some of the uh, COVID-19 analytics that he has been doing. Thanks and welcome, Fred.
Thank you, Luciano. So, hello, everyone. I will endeavor to keep this video running, although I may have to drop it, but for now you can see my face. I'm Fred. I work for IBM. Officially, I work for, well, HR thinks I work for IBM Research, but it would be more accurate to say I split my time between IBM Research and open source at IBM. That means that I get to work on exciting projects like the one I'm going to talk to you about today, the Elyra project, and our work on notebooks for analyzing COVID-19 data. As far as my own, how I got to where I am, so I started out in IBM research. I went to grad school at UC Berkeley and then joined IBM in 2006 and worked just for IBM research for 9 years. And then I joined a new organization we were calling the Spark Technology Center, which was focused around software for analyzing large amounts of data using a technology called Apache Spark. And since then, our organization has grown to encompass a larger mission, including end-to-end data science, including Jupyter Notebooks, which I'm sure many of you use on a daily basis in your classwork and research work. So I'm going to share my screen here. And by the way, we have also on the call Luciano, who did the introduction, and Kevin Bates, also from our team, who are working very hard on a project that we call Elyra, which is part of the Jupyter ecosystem. Let me bring my screen up. So if you want to find out the details about Elyra or try it out, the website is Elyra, that's ELYRA.readthedocs.io. And it's named after the least popular moon of the planet Jupiter, except spelled with a Y instead of an I. And this is a project that aims to make some extensions to JupyterLab to make it work better for people who use JupyterLab in their jobs, as opposed to as an educational tool. So if you use JupyterLab to do professional work, there are several things that are different in that kind of a situation. Number one, you have to work with other people. Number two, you need to keep track of your work products because they're part of your business, and you need to share those things with other people. And number three, you're going to need access to big data, big machines, because professional data science often involves really large data sets or building really large models, and you need to manage getting access to those machines, which may not be the machine that you have sitting on you in front of your desk, but maybe someplace off in the cloud. So in Elyra broadly, we have a bunch of extensions to Jupyter that we bundle together to make using JupyterLab for work better for professionals like the people, the data scientists in our organization at the Center for Open Source Data and AI Technology. So in particular, things that come with Jupyter, and you can see on my screen, we have a way of connecting together multiple notebooks into a cohesive pipeline. So if you have a notebook that gets data and another notebook that cleans the data and another notebook that analyzes the data, you can run all of those at the same time as a pipeline. We have the ability to connect up this pipeline workflow construction to the cloud so that you can have a whole bunch of very compute intensive notebooks, stitch them all together, and send that computation off to the cloud to run on a big machine while you do other work on your laptop. We also make it easier we have what we call hybrid runtime support, which lets you run a notebook interactively, but have all the computation in the notebook run on a bigger machine than your local laptop. Now, again, off on the cloud. Sorry about the printer in the background. Other things we have are better support for versioning and navigation of notebooks, so that when people working on a team, when you work professionally in data science, you're often working on a team. When people are working on a team, they can share a repository for all of the notebooks that they're working on and manage changes or potentially conflicting changes on those notebooks so they can all work together. And we also have notebook navigation automatic generation of table of contents, so it's easier for one person to pick up another person's notebook and know what's the general outline. So all of this is stuff we've been working on for a couple years to help, primarily to help IBM's customers to better use Jupyter notebooks in their own enterprises. And we've been doing this all in the open. Again, the project is Elyra, that's Elyra. And to showcase the benefits of this for team data science, professional data science, we put together a series of notebooks. Actually, we got all the data scientists on our group to kind of pool the notebooks we had been creating separately, either for our own personal edification or to demonstrate how to analyze COVID-19 related data. And we created this open source project that we call not terribly creative, but COVID-notebooks. And this is all up on GitHub under our GitHub section. That's CODAIT, Center for Open Source Data and AI Technologies /COVID notebooks. And this is where we have put a whole bunch of notebooks, Jupyter notebooks, that walk you through the process and act as a starter kit for doing your own interesting analysis on all of the data that's available for the COVID-19 epidemic. And so if you download this project to your local machine and run the instructions at the right here, yes, to configure a local development environment, you'll get an environment like what I have over here in this window, which lets you fire up a copy of JupyterLab, which looks a bit more probably looks like the JupyterLab you're familiar with, but this also has our Elyra project extensions added into it. So you'll notice, the first thing you'll notice is that logo up at the top right is now an Elyra logo, just to indicate that you've got some extra stuff in your JupyterLab. The second thing is there's a couple of additional extra tabs down here on the left. And the third thing, the big thing, is we have the capability to make pipelines from multiple notebooks. And this pipeline that you see on the screen right now is the pipeline that our data scientists have put together to do analysis on county level data for the coronavirus outbreak in the United States. We also have a second pipeline that you can again pull from our repository, that does a similar thing, but for data from the EU Center for Disease Control's worldwide data set at the granularity of countries, nation states. Today, I'll just walk you through the US pipeline and give you an introduction to what is going on here. Now, anytime that you're doing data science or work, it's a bit of a different process than if you're doing data science for a course. Because when you're studying data science in college, that study is necessarily going to focus on techniques, and in particular on the more advanced techniques, things like machine learning or probability and statistics. When you do data science professionally, the hardest part of that process is getting data. And the second hardest part is translating the questions you have that you're trying to answer that data from the kinds of questions that you would ask a person to the kinds of questions that you would ask a machine. And a lot of the flow that you're seeing on this screen right now, a lot of the code that's involved here is on just the acquisition of that data and getting the data into a format that's amenable to analysis. And in fact, a lot of the benefit that this repository provides you is as a starter kit that takes care of a lot of those initial steps. Because as you'll see as we're walking through this, we had to do a lot of work to get you to the point where you have a roughly clean set of data to start out with. And one little data point to bring up here, let me just unshare my screen so that anyone who's watching the recording will actually be able to see this, is that it's really hard to get high quality data about this outbreak. There's lots of data around, lots of very talented people are producing it, but it's really hard to get high quality data. So this morning on the front page of the Wall Street Journal, there's this map of deaths from coronavirus in the United States. And if you go up here and look very closely, I don't know if you can see it. There we go. The state of Rhode Island is marked as having 0 deaths. And if I share my screen again, Rhode Island Department of Health strongly disagrees with that, in fact, and is recording 677 fatalities from COVID-19 in Rhode Island. So if the front page, literally the front page of the Wall Street Journal, can have that kind of a hole in its data, it's really hard to get clean data on this outbreak. And you have to work very hard to obtain that data, to verify that it's clean, and to, in many cases, pull in data from multiple sources to synthesize a clean starter data set. Let me show you how we go through that in the context of our overall flow. So the very first thing that we typically run, and this, by the way, the underlying data changes every night. So I run this, every time I want to see updated charts, I have to run this entire flow, which is why we have a workflow. But the first step is to what we call ETL, that's extract, transform, and load, acquiring raw data. And that's done by this notebook here. And we're using, in this notebook, we're acquiring data from two data sources for the reason that I just showed you on the front page of the Wall Street Journal, because there are some, the primary data source that most people use for data on this outbreak is the Johns Hopkins repository, which you can see here. Just search for Johns Hopkins COVID-19 GitHub and you'll find this repository. These guys publish fairly reliable data about the entire US at a county level, but there are significant gaps for which we have a secondary data source. We use the New York Times' parallel repository of COVID-19 data, which is called COVID-19 data under New York Times on GitHub. We use that to fill in some of the holes, and we use other sources to fill in some additional holes. And I'll show you that when we get to the data cleaning. But basically, what we have to do here is just to download the data set and write it out as a CSV file that you can then analyze with pandas. We have to do all of this code. Because when you work in data science professionally, the hardest part is getting the data, and there's a lot of code involved in getting the data. Now, fortunately for you, if you use this repository as a starting point, a lot of this initial work will be done for you, but anytime, if you have to dive back into it to answer a specific question, there's going to be a lot of time spent on acquiring data and cleaning data, and that is perfectly normal. That is part of the process of doing professional data science, like for a living. So at the end of this notebook, we write out some CSV files, which end up looking like this. And this is the time series for every county arranged vertically. You can see the first column holds dates, and the first, however many rows it is, probably about 80 rows, are going to hold the confirmed and deaths and recovered time series for the first county, which is Autauga County, Alabama, in alphabetical order. And you can see that going up as time moves forward. And we do that for every single county in the United States. So that is our first stage of analysis, ETL. Now, I should mention, by the way, this is an entire cohesive workflow, and we can, by pushing this button up here, run the pipeline on the cloud, and our technology makes that super easy. And it just basically what happens is in the background, the Jupyter server that's running on my laptop is talking to our server on the cloud and packaging up all of the auxiliary data that goes along with this entire workflow and sending that off to run on the cloud. And later, once all these notebooks have run, some of them are quite compute intensive, we'll get back some results from that cloud run, and we can see that on the cloud server. For the moment, I'm going to stick to my laptop where we've got a cached copy of the reasonably recent runs of these notebooks. So I showed you ETLing, extracting, transforming, and loading the US data. That is just the very first step to get the raw data from those two data sources. After that, we need to clean the data. And for that, we have this second notebook, which we call cleaning data. So there are a couple significant holes that you'll find in the Johns Hopkins data set. First one is Rhode Island, like I showed you on the front page of the Wall Street Journal. The time series for deaths in Rhode Island look like this in the Johns Hopkins data, and that is not correct. So we need to go in and take that raw data set I showed you and substitute the New York Times numbers, which look like this. Still not clean, but at least they are monotonically increasing, and at least the totals roughly match up with the Rhode Island Health Department. These time series for what was in the Johns Hopkins data set. And there is a similar set of holes in Utah. Again, on the front page of the New York Times, we have a very incomplete picture of Utah. That's because the Johns Hopkins data they built that map off of has a very incomplete picture of Utah. So it looks like this for Johns Hopkins. You can see there are some cases where the confirmed cases goes up and back down to zero. New York Times is, again, not perfectly clean, but cleaner. So we use that data for Utah. Then there's New York City, where Johns Hopkins and also the New York Times numbers both code all of New York City as being in Manhattan, which is, of course, not correct. Most of the population of New York City lives outside of Manhattan. And so, but if you code all of New York as being in Manhattan and you try to analyze, say, the amount of people infected per capita, you will get very strange numbers. So what we do in this data cleaning script is we download a third data set from a small New York newspaper called The City, which aggregates data from the New York Health Department. And that gives us time series data at the county, or in the which in New York aligns to borough level for New York. So we go from having a time series for confirmed cases and deaths in New York, where there's like one New York, and that New York is coded as being just Manhattan, to having 1, 2, 3, 4, 5 different time series for confirmed cases and 5 time series for deaths, with actually very different, well, somewhat similar. You can see there's a similar shape, but significant differences in the outcomes for each of these 5 boroughs, as we'll see in just a moment. So it's important to be able to break down even just New York City into the different components. And to do that, we had to acquire additional data. So again, doing data science professionally, data acquisition, negotiate to get data, figuring out where data is hidden, downloading it and formatting it is the majority of the work that you end up doing. So those first 2 stages of our pipeline here, ETL and clean, and there's also a parallel process for census data so that we can, our job has finished uploading its auxiliary data files. And so results will appear here. So now we're running these notebooks on the cloud in the background. I hope I enabled my VPN. There we go. Okay. Yeah, running data intensive stuff and a WebEx meeting at the same time is a little risky, but you can see our pipeline has started running on the cloud using Elyra to push all of those notebooks to the cloud and have them run there in the background so I can do other stuff interactively on my computer in the foreground. So while that's running, let me show you. There's this second extract, transform, load phase that we do for census data. Because if you have time series about counties, about how the outbreak is proceeding in counties, you would like to be able to put that data up alongside things like what is the population of the county, what is the income distribution of the county, what are the demographics of the county, how densely populated is the county, because these factors significantly affect how you would interpret, say, a number of confirmed cases, and how you would predict that that number might change in the future. The US Census provides enormous amounts of data, but, and you'll see this as a common theme, actually obtaining that data and getting it into a format where you can use it is a huge amount of work. This notebook, in fact, is still something of a work in progress. We've gotten the income data out, but you can see the amount of code that we had to write just to get the income data out. And we're still working on the demographics. Census data comes from, you can get it from data.census.gov, a website that I think was written by the lowest bidder, but if you drill down and manage to convince this website to give you a particular data set, you will get back something that looks like this, an incomprehensible name wrapped around a data file which has many, 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 many different columns with headers that you need to actually decode, because these headers, these names have an implicit hierarchy encoded in them. Anyhow, if you want to find out all the minutiae of how you decode this file and turn it into something you can actually use to join with the COVID-19 time series, that process is outlined in this second notebook, our ETL extract, transform, load notebook for US Census data. And we walk through each of the steps of decoding this income data set. And once we've had a little more time to work on this open source project, we'll also do that for the second data set of social characteristics. You can see we've actually started the process here of decoding the columns, but we haven't pulled out those histograms. What this census notebook gives you is, at the end, we output these income data by county for the United States. The histogram of income. So first, each one line per county, and then we have a histogram of several different buckets of income and percentage of households in the county that have, in this case, less than 10,000, 10,000 to 15,000, 15 to 25, and so on. We also have aggregates, mean and median income in dollars for each of the counties in the United States. And that lets you do interesting things like track how the epidemic has been affecting demographic groups with different levels of income. And which gets me to the third part of our pipeline, which is where we take that census data and that cleaned time series data, and we can combine them together in this notebook on demographics. And now this, I should caution, is just a starter kit. We're showing some of the analysis you can do. There is a whole lot more analysis you can do beyond this once you have the data in hand. This is just kind of showing you some of the stuff you can do relatively easily once you have that data in hand. I don't think I've rerun this local copy, so I will run this notebook myself on my machine. So if we read in our clean data about the time series for each county and that income data that we pulled out of that census data source, then from there we can get to moment while it loads up. $3,000 time series was 80. There we go. Okay. Yeah, actually it's 1, 2, 3, 4, 5, 6 different time series, because one part of the data cleaning script I didn't show you is we automatically identify certain points that we haven't been able to clean, like cases where the number of deaths goes up and then down, as outliers, so that follow-on analysis can avoid using those to draw conclusions. So we have confirmed deaths, recovered, and outlier masks for all of those. So a bunch of time series you need to unpack to get to the point where you can analyze. But once you have unpacked everything and you've joined in with, say, population statistics from the Census Bureau, you can group the counties in the US into deciles by population. Decile is the counties, the 10% of counties with the smallest population have population from 0 to 5,000. And the next smallest 10% have population from 5,000 to 800, and so on. 10% most populated counted have population above 213,000, and so on. So we can take each of these bins of population and compute a time series in aggregate for those, and then graph that, and it looks like this. So here are the number of confirmed cases of COVID-19 in terms of population for each decile of counties. So this red line here is the top 10% of counties by population. You can see they have a huge number of confirmed cases. That's largely because they have a huge population. What we can do to correct for that is to normalize to the population and then take And then you start seeing a different picture, right? Confirmed cases per 100 residents broken for buckets of counties broken down by population. The reddest line here is the most populous 10% of counties. The bluest line is the least populous. You can see there is still the confirmed cases are still concentrated in the most populous 10% of counties, but the remainder of the country is actually closer than it would look looking at the absolute number of confirmed cases. And if you bring in that other census data in about income, and we break down counties according to decile of income, the 10% highest, the 10% of counties with the highest income, the next 10%, and so on, then we can see that if we run the same graph, a little bit of data analysis needs to be done to get to the point where we can run the graph. But once we do that, you can see the number of confirmed cases broken down by median income. Red is higher median income, blue is lower median income. It looks like the outbreak is concentrated in the most wealthy counties, but that's only because wealthy counties, while the counties with higher median income have higher population density because they have a lot of cities with high cost of living. If you normalize the population, the picture looks very different. And in fact, the highest concentration of confirmed cases is in the second, I think, yes, the second lowest income bracket of decile of counties when you confirm. So we go from it's a rich counties, a disease that's concentrated in rich counties, to a disease that if you normalize the population is actually quite prevalent in some of the poorest counties in the United States. You get very interesting points of view when you combine multiple different data sources. Now, I see it's 11:29. Do we have half an hour or 1 hour to talk about this?
We have an hour set aside for this, so you take as long as you like, Fred.
Okay, Zach.
If others need to leave, go ahead.
Sure. I'll do a couple more minutes to give a quick walkthrough of the remaining notebooks, and then I'll open the floor to questions, because I'm sure some people listening in have some questions to ask.
That'd be great. Thanks, Fred.
Sure, no problem. All right. So we talked about loading data and how hard it is to acquire data. How we have to go to multiple data sources to get accurate time series of somewhat accurate time series, I should say, of COVID-19 cases and deaths, and how we have to clean that data extensively to get to the point where it's not really obviously wrong. And also how we have to go through quite a bit of work to get demographic data to load up with that. But then we showed you how when you do get all that clean data together, you can come to some very interesting conclusions. And again, these conclusions, like what we saw here, we're just scratching the surface. There are lots of other bits of demographic information you can combine together to get interesting pictures of what is going on as a result of this pandemic. And I would encourage you to try downloading these notebooks and doing your own analysis. This is intended as a starter kit for you to do your own work. We've focused mostly on the data cleaning. Let's go through some other examples of things you can do that we've included here. So we talked about using demographic data to graph some of those time series. We can also use like population data to do maps, to generate what are called choropleth maps. These are maps that are coded these are rather graphs, where the graph is a map where each part of the map is coded with color to indicate the value of a variable. And you probably see these a lot. It becomes clear when you see it on your screen. Here is the map of confirmed cases in the United States. I think this is from last week, but it's not changed that much since then. Yellow is pegged at the 95th percentile. And this probably looks familiar to you. What may look a bit less familiar to you is the same map, except we've pulled in some demographic information and normalized the number of confirmed cases to population. Let me put them both on the screen at once. You can see, even broadly, there's a bit of a difference, right? The normalized map looks a bit more gradient-like. This one has a very harsh drop between cities and rural areas. When you normalize the population, you can see, in fact, almost the whole country is affected. Other things to point out are, if you look at California, on the absolute case numbers, the picture is very different than if you look at case numbers that are normalized to population. In California, that effect is particularly significant because, as you can see, California counties are, for the most part, huge. Well, your county in San Luis Obispo is not that large, but San Bernardino County is this entire region of the state. And so these counties have very high population, which means they have very high case numbers. But if you divide that number of cases by the population, the outbreak is actually not that far advanced in California. Whereas if you look at the lower right here, down in the deep south, you have these sparsely populated rural areas wherein the absolute case numbers are not that bad, but the case numbers relative to population are actually quite concerning. So again, this is just one kind of analysis you can do, drawing maps based off on this data. There's a huge variety of other things you could do. You could take this code and copy it and modify it to do other analyses, and I would encourage you to do so. But again, we're looking at a very high level view here. So let's pop back up to our main flow and talk about some other things you can do. You can generate tables. You can just use plain old pandas data frames to slice and dice this data. And let me rerun this so we get updated results here. So our raw data set, of course, is time series for the counties. We can just pull the last element of those time series, as we do right here, to get the most recent case numbers for every county in the United States, which gives us a useful data set just to aggregate down to different levels of granularity. So we can group those counties by state and get total case counts for each of the states. And then we can sort those case counts to get top 10 states by confirmed cases, or by confirmed cases per 100 residents. And here's another interesting thing to point out. You look at the top 10 states by confirmed cases, and it's a pretty familiar set. New York is at the top, followed by New Jersey, which is right next to New York, then Illinois, where Chicago is located, California, which has a lot of people, and so on. But if you look at the top 20 counties by confirmed cases per 100 residents, the picture is very different. Tennessee, Nebraska, Arkansas, Minnesota, Tennessee, Nebraska, Kansas, Oklahoma. Very different picture if you look at the data in this different way. And there are, of course, many other different ways you can look at this data, and I would encourage you to, again, to use this notebook as a starter point and try and slice and dice this data on cases by county and look at all the different bits of information you can get out of it. So we can build tables, we can join in demographic information. We can also analyze, instead of analyzing every decile of the counties for time series, for aggregate time series, we can analyze the individual time series, which is what we show you how to do in this starter notebook we call time series US data. I will rerun this one too, so it gets the latest data. So what we're doing in here is we're reading in, again, that same data, cleaned time series data from our data cleaning script. And then we collapse all the time series down into each time series into a single cell of our pandas data frame using an extension to pandas that comes from a project we have done called text extensions for pandas. This is still kind of bleeding edge stuff, but if you go to GitHub under CODAIT/text extensions for pandas, you can try this out. What we do is we extend pandas with data types that are useful for natural language processing, which would include ways of representing spans within text, but also ways of representing tensors and multidimensional arrays, because tensors are very important for modern text processing. Well, tensors are also very important for modern data processing of time series. So in this notebook, we use our tensor type to collapse the time series for each each county in the US down to a single cell of a pandas data frame. And then we can manipulate all those time series almost as if they were scalar values. So we can go and sum all of the time series in the confirmed cases column and plot that directly, and that will give us the total confirmed cases plot for the US. Or we can break up those the elements of this confirmed these time series according to whether they're either in New York City or in one of the counties adjacent to New York City, or if they're in the rest of the country by just doing we build up a mask by saying whether the FIPS code, by the way, is a code that the Census Bureau developed in, I think, the 1960s to encode every county in the US as a integer. And we use that as the index to all these time series because that's what Johns Hopkins does. So if we use those FIPS codes for New York and adjacent counties, we can pull out just the time series for those and add them together by just taking a sum as if they were scalar values. And we can do that for the ones inside New York City and its surrounding areas and outside of the New York metro area. And that gives us this plot where we have, again, the entire US inside New York City or counties adjacent and everywhere else. And you can see, again, there is another interesting insight from the same data set that the outbreak in terms of confirmed cases is really tailing off inside New York City, but not so much everywhere else. But the sum of those produces a plot that looks like it's tailing off even when that primary component of that tailing off is actually, of that reduction in rate is actually entirely localized to New York and surrounding counties. But of course, this is aggregating time series like we were doing before. We can also plot all of the time series on the same chart, which looks like a bit of a mess. Actually looks like a bit more of a mess if we use a semi-log plot where the y-axis is logarithmic. But if we do some more manipulation, and you can, by the way, see all the code that we did to use this manipulation at your leisure. But if we do a bit more manipulation, we can start to get the time series looking a bit more organized. In this case, what we've done is normalize to population. They start looking like the disease is following a similar trajectory across counties, but you see that the different counties are starting their outbreak at different points. Well, we can correct for that by shifting time series forward and backwards in time, which produces plots that look like this. We have this defined, in this case, day 0 to be when a given county breaks the number of, in this case, confirmed cases that Manhattan County had on March 23rd. And if you align all the time series so that day 0 is that point in time, they will, of course, all cross each other at day 0, and you have a trajectory before and after day 0. And you'll notice that different lines on this chart are different colors. The color in this case encodes how far we had to shift each time series to get day 0 to line up there. And you notice there's a significant rainbow effect, which you see even further when we have a log scale on the y-axis. The counties that we shifted more, the ones that had an outbreak later, crossed that threshold at a shallower slope. Why exactly that is, I'm not sure. We'd have to look more at the data, but that's another interesting data fact that we can get out of this data, that later outbreaks had a shallower slope, at least in terms of absolute confirmed cases. Here's in normalized to population. There still is a rainbow effect going on here. So even if you normalize to population, later outbreaks have a shallower slope at the rate of infection. The other thing that you can do with all of these different time series, and which we show you how to do in this series of 2 notebooks, is instead of looking with the Mark I eyeball to analyze each of these time series by just looking at graphs and changing what graph you generate, you can have the computer characterize the time series so that you can divide them up into buckets that are objectively different from each other. And the way we do that in this notebook is by fitting curves. We define families of curves, and we use scipy.optimize and basically gradient descent to ask the computer to find the best curve from each of those families that comes as close as possible to the underlying time series. And the parameters of those curves, things like the slope of the curve, the rate of exponential growth, give us objective metrics about the past history of the outbreak in each of these counties, which we can then use to filter or analyze the counties themselves. So the machinery to do this kind of curve fitting gets a little advanced, but we walk you through it in this notebook. So we start out with fitting. How do you fit a straight line using the optimizer that comes with scipy.optimize? You need to define an objective function. You need to define what is the function that you're trying to fit, and then feed it through this function, scipy.optimize.minimize, which runs an algorithm called LBGFS, which is doing it's using first and second derivatives of your curve and your objective function to try and find a optimum solution. And if you use that technique to fit lines to each of the time series, you get charts like this. Obviously, most of these time series are not actually well characterized by a straight line, but that's the best you can do trying to fit a straight line. Later on, we look at different series, different kinds of curves. We look at exponential curves, where you have assume how well does an exponential function explain each time series. Logistic curve is a curve that starts out exponential and then starts to tail off as it approaches saturation. And we also look at mixtures of logistic curves, and that gives us fits that look like this for exponential, or for logistic curves, which tail off, start to get closer. And when we have more parameters and we're fitting mixtures of curves, we can get especially close fits. This is just using these curves to characterize the time series. Once we've done that, coming back again to our top level, we can take the output of this curve fitting exercise and analyze it, use it to break down the time series into categories. And this is where we start getting some interesting insights. So again, we fit all these curves from 3 different families: exponential, which starts small and then grows really fast; logistic, which grows exponentially and then tails off; and mixtures of 2 logistic curves to model cases where the time series is explained by starting on one logistic growth process and then shifting to another because something in the underlying epidemiology of the county has changed. So we have fit these curves to each of the time series, and by looking at the goodness of fit, how well does the best curve from each family that we found fit each of the time series, we can kind of categorize the status of the outbreak in each of the counties in an objective fashion and get a good picture at a broad level of what is the past history. These are not predictive models, by the way. These are models that describe the characteristics. So for example, if we look at the counties where logistic growth which tails off, provides a much closer fit than exponential growth, that bucket of counties, broadly speaking, has shaped curves that look like this. The blue line is the best exponential fit, and the orange line is the best logistic fit. You can see counties where the fit for logistic is much better than the fit for exponential are counties where the outbreak has this characteristic that it has tailed off. And that is a useful bucket of counties to be able to identify quickly. This is one way of doing that. If you can also look for counties where the fit with 2 logistic curves mixed together is significantly better than the fit with 1 logistic curve, that's an indicator that you cannot explain the progression of the outbreak in that county by simple logistic growth. Something more complex is happening underneath. You can see these curves have more complex shapes. Again, that's an interesting way of identifying some time series you'd want to do some follow-on analysis to. And my favorite thing that you can get by sieving these time series according to goodness of fit is to look at the time series that don't fit any of these curves well. And that is a good way to find what appears to be dirty data. So time series that for no explained reason have sudden jumps up and down, time series that go down when the number of confirmed cases is supposed to be a total over time, and that should never happen. So by looking for things where the computer was unable to find a good fit, you can find cases where the underlying data is itself suspect, and there is room to do more of that data cleaning that beyond what we've already had to do just to get to this point. Bringing me back to my original point, which is that when you do professional data science, when you're doing data science for your job or for a nonprofit, the number one task, the one you spend most of your time on, is obtaining good, clean data. And you can see why, because every time you do analysis, you go through several stages of analysis and you come right back to, this is the point where I need to clean my data some more so I can do my next stage of analysis. So again, we've been working here in the context of this workflow, which is described in a pipeline file in our pipelines directory, which is inside in this case, my local copy of, not that repository, but not repository, excuse me, come on, WebEx, of this repository on GitHub, CODAIT/COVID notebooks, where we have a bunch of notebooks, Jupyter notebooks, that give you a starter kit for downloading, cleaning, and analyzing COVID-19 time series data. So that's the whistle-stop tour of our code our open source code that we've shared, which uses our Elyra project extensions to combine these notebooks together into a workflow. And hopefully that gives you a high-level picture of what we've got here and what processes we had to go through, and how much of the work that was involved in putting together the data science here was on the data as opposed to the science. So we got about 11 minutes left. I think it would be a good time to maybe open up the floor to questions.
Yeah, I had a question. When you showed the graph with the countrywide cases with New York kind of separate out from them, like that countrywide graph looked pretty like close to linear. And I was wondering if based on like the other analysis that you showed in that last notebook, if that is mostly from like sublinear countywide curves being added with like superlinear ones, or if there is like a lot of counties that are just basically straight lines.
So the modeling for that, where does the straight line come from, is extremely complex. And there are a lot of epidemiological teams around the country. I should note, by the way, I am not an epidemiologist. I'm a data analysis person. But there are a lot of actual experts on epidemiology having a impassioned debate on what exactly is behind that straight line. As far as I can see from looking at past data, it is the superposition of a lot of logistic curves that just happen to average out to overall roughly linear growth. There are also quite a few counties that are experiencing what looks like a linear growth, which in terms of the underlying fundamentals would mean that for every person that gets infected, on average, one person gets infected by that person. But although the time series for the entire United States looks like that, either the tailing off for New York and surrounding counties or growing linearly, the individual counties, heck, I can go back to the notebook I was just looking at. The individual counties are not at all, clean like that. It's just that the one county having a sudden uptick is canceled out by another county tailing off. And with 3,000 counties to draw from, the average looks pretty smooth. I'm sure you could do some more analysis, slicing and dicing this data to get at a more fine-grained answer to that question. I'd encourage you to do so. We provide the the basics to start out. And are you Logan, or is that just your screen name?
Yes, I'm Logan.
All right. Thank you, Logan, for the very good question. Yes, and something I puzzle myself about a lot. Any additional questions? By the way, you may need to unmute yourself.
Hi, Fred. I'm Tim. And I was wondering, when you ran the notebooks in the beginning of the simulation, and it was spawning some Kubernetes stuff and running it, is that all pre-set up with Elyra, or would I have to, if I'm running Elyra, do I configure that and set it up to a AWS account, or how am I connecting to the cloud compute with this setup?
So I could answer that, but maybe Luciano, who is more of an expert on this, would like to give an answer. Luciano, are you there?
Hey, team. Hey, Fred. Yeah. So we delegate with Elyra, we delegate the execution of the pipeline to supported runtimes. And we have added a capability for you to actually configure those external runtimes. So if you have, let's say, a Kubeflow pipeline or something that is available somewhere, and you want to add to that, you want to run your experiments in that environment, you just need to configure that, which currently is via command line, but we are adding a UI for that. And then all the execution will go there. If when Fred, Fred, if you go to your pipeline and just hit the submit, yeah, you will see that you have a list there that you can select runtimes. Like in my case, I would have maybe 2 or 3 because we have different versions to make sure it runs with different versions, and those can be on any accessible cloud or things like that.
The particular one that I was using is this Kubernetes cluster that is on the IBM cloud, but you could configure this to point to the Kubernetes cluster running on your local machine if you just want to get background operation, or on AWS or anywhere where Kubernetes is supported.
So you could point it to your own Jupyter server that you've already launched if you wanted to. Like if you wanted to run it on locally.
You could point it to your own Kubeflow pipelines instance, definitely. And we're getting support for Airflow. What's the status of Airflow support, Luciano?
We have a PR that is functioning end-to-end with some limitations, but it's almost there.
Okay. Yeah. So so Kubeflow and soon Airflow, if you can get one of those workflow services up and running, either on Kubernetes, on the cloud, or on your local machine, or on a machine at your university, then you can point Elyra, all of Elyra's batch processing facilities at that system and offload work to the cloud that way. You also can configure Elyra's remote kernel running to use a cloud machine to run all of your notebook kernels, where each kernel runs inside a separate container. So that's useful if you're doing things like training deep learning models, where you want each of the notebooks that's running in your environment. Right now I have like 10 notebooks open. If you wanted to have half a dozen notebooks open, training half a dozen different models at the same time, you can have those notebook kernels running on half a dozen different machines, each of which has its own GPU for acceleration. So yeah, it's a really great capability when you're doing data science for work, and you got to work with a team of people, and you have to work on big data, and you're on deadlines. So being able to push work to the cloud, really important. So thank you, Tim, for the great question. Now, I think we have time for one more question, and then we're going to have to wrap up. Any takers? If not, then I think we can probably draw this call and this recording to a close. So once again, I'm Fred Reiss here with Luciano and Kevin from our team at. Oh, is there someone else?
I have one question from Jay. Were you trying to say something?
Yeah, sorry. I was gonna say about like getting the data like the US data and all the census data. How are you getting those data, like, to analyze them? Like, are you getting from the API, through the API from the URL, or?
That is a great question. What is the physical process of obtaining that data? And it's super important because, as I said, obtaining data is a huge part of any professional data scientist's workflow. In the case of the census data, they put it behind this site where the only way to get it is to convince the UI to give you a download data button and then download the file, and then that gives you a CSV file you have to decipher. The more user-friendly way, which a lot of data sources for COVID-19 are switching to, is there is a GitHub repository which contains a CSV file which is updated every night. And if you look in ETL US data in the first cell here, we provide links to the 2 repositories where the data files are located. So if we go here to Johns Hopkins, the actual live data is in GitHub in this directory, CSE COVID-19 time series, and it's one CSV file, which is gotten too big for GitHub to display. There's what it looks like. The time series is sprayed across a whole bunch of columns, and you need to decode the column names into dates. But we provide code for doing that in this notebook. The New York Times, likewise, on their GitHub repository, they store the time series, and I forget exactly where that's located, but they have a helpful link directly to the raw CSV file. And basically, you point pandas at this file, and it will give you the shredded, in this case, time series. So you got dates, cases, and deaths. That's the US one, but there's a county level right here, which is shredded vertically: date, county, state, FIPS, integer code, cases, and deaths. And this into pandas, and again, you can reorganize it into something that's actually amenable to analysis by indexing and pivoting to get to the time series themselves.
Okay.
We had to do a similar thing with the New York borough level data, which is in a 3rd GitHub repository in a 3rd different format. But with a couple lines of code with tools like pandas, you can massage all these data sets into the same format and then start combining them together. I should note, by the way, that pandas will let you take raw GitHub URLs like this one right here, raw.github.usercontent.com, and just pass that directly to pandas.readcsv. And that's a super, super useful feature. Anytime you're dealing with like live data that people are sharing by GitHub, you just point at the GitHub URL and it just works. So I see that we are coming up on the end of the hour. If you have any other follow-on questions, please shoot us an email or send us a pull request or open an issue on our repository. Once again, that repository is under CODAIT on GitHub, and it's COVID-notebooks, where we have all these notebooks to provide a starter kit for doing your own analysis on this very important and interesting time series data. So thanks again, everyone.
Thanks, Fred.
Thanks so much, Fred. Yeah, thank you,
Fred.
Fred, for taking the time. Thank Luciano for setting this up too. It was a lot of fun.
Okay, thank you all, and see you guys on the community. Thanks, bye.